Students, this lab is called the Shifting Equilibrium lab. And in it, there are two parts. The first part is going to involve vials of potassium thiocyanate, iron 3 nitrate, and sodium bisphosphate, or NaH2PO4. We're also going to need 6 test tubes in a test tube rack, a bottle of deionized water, a couple of pipettes, a 50 milliliter beaker, a test tube holder, and then I have a beaker of cold ice water and a beaker of hot water that's warming up here. In part 2 of the lab, we'll use the other 3 vials, which I'll describe at that time. The first thing we're going to do is set up our hot plate and cold water plate. Then the directions specify that we should take our 50 milliliter beaker and add some water to it. Deionized water. I'm just going to pour from the bottle because it's a little faster. I'll fill it up to the 40 milliliter mark like the directions say. And then directions say, take the vial of iron 3 nitrate, and I'm going to shake it a little bit so that it, any sediment at the bottom will be mixed up in solution. And it says transfer 1 milliliter. So I'm going to take my 1 milliliter plastic transfer pipette, and I'm going to squirt it into the deionized water. It then says take the vial of potassium thiocyanate, and I'm going to use my other plastic transfer pipette to transfer 2 milliliters to the 50 milliliter beaker. Now, try to watch the color change. Right now, it's a faint yellow. And as I added the potassium thiocyanate, it changed to a dark red. That was only 1 milliliter. Now I'm going to squirt another milliliter to the 50 milliliter beaker. I'm then going to discard one of the 2 plastic pipettes. It doesn't matter which one. If I throw away one of them and keep the other one, I'm going to mix the contents of the 50 milliliter beaker. So the dark red material is going to get mixed up. And I'm going to transfer 1 milliliter to each of 6 test tubes. So I've got 6 test tubes in a test tube rack. And I'm going to use my dark red solution and transfer 1 ml to each one of those. And we're just looking at color changes, so I don't really need to measure this too carefully. I want to go for the dark color in each of the 6 test tubes, and then we'll set that aside. Okay, so now I'm going to set aside my small beaker with the dark red material. And let's number the test tubes from left to right. So test tube 1, 2, 3, 4, 5, 6. It says to test tube 1, add 10 drops of deionized water. This will be our control. So I'm going to screw the squirt portion back onto my deionized water bottle, and I'm going to carefully add 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so and we get kind of a, I'll hold this a little closer for you. We get kind of a dark red. That's going to be our control or standard of comparison. Then we're going to add 10 drops of iron 3 nitrate to test tube 2. And again, I'm going to swirl this a bit, and I'm going to add 10 drops. 1, 2, 3, 4, 6, 7, 10. And I get a similarly dark colored solution. To test tube 3, we're going to add 10 drops of the potassium thiocyanate solution. 2, 3, 4. And I'll swirl to mix. To test tube 4, we'll add, again, 10 drops of deionized water. To test tube 5, we're going to add, let's see, for test tube 4, it was 10 drops of deionized water, and then we're going to place it in the ice water bath. So my larger beaker with ice water is going to hold test tube 4 temporarily while we observe a color change. To test tube 5, I'm going to add 10 drops of water, and I'm going to place it in the hot water bath, the beaker here. And then to test tube 6, we're going to add 10 drops of sodium bisphosphate, NaH2PO4. And we're going to notice what differences we can find. Notice that with the sodium bisphosphate, the color went from a dark red to an almost kind of a cloudy white color. And we're just going to see what kind of a comparison we can make. So if we review the colors here, here's test tube 1 with just water added and no temperature change. Here's test tube 2, where we added some iron nitrate. Here's test tube 3 with potassium thiocyanate, and I'll kind of put these next to each other. Test tube 4 is in the ice water bath. I'll retrieve that right now so we can see any color changes here. It's a slightly lighter color than it was before due to the color change. And then at test tube 5 in the hot water bath also has changed color a little bit. And what we're doing in each of these cases, students, is shifting the equilibrium. We're making, with an awareness of how the reaction works and whether it's endothermic or exothermic. And the reason we pick this reaction is because there's a visible product, and so the intensity of the color reflects the amount of product that we can see. So that's part 1 of the lab. We'll pause now and begin part 2 in just a couple moments. Now for part 2 of the lab, we're going to begin by adding approximately 2 milliliters of deionized water to a clean test tube. We only need 1 test tube for this. So I'm going to start by just adding a little bit of water to a test tube. Then I'm going to add to that an indicator solution. This solution is called bromescal green. And it's the reason we call it an indicator is because it has a different color based on the pH of the solution in which it's found. So we're going to add 5 drops of bromescal green to the test tube. Let me hold this close to the camera here. So if I swirl this, you can see the green mixing in with the rest of the solution, and eventually we get kind of a greenish color. The color is, or the name bromescal green is appropriate here, right? Okay, so it's kind of a light green color. Let's see what happens if we add a few drops of 0.1 molar hydrochloric acid. So if we make the solution acidic, what's going to happen to the color of the solution in the test tube? So it was green, it's getting more and more yellow now. If I swirl this, it's a little more obvious. So we went from green to yellow upon the addition of acid. Now we're going to add some sodium hydroxide until we get a little bit of a greenish, or we may even transition to a blue color. So I'm going to try to hold this close to the camera here. Watch the colors. So we went from a yellowish solution to, if I'm swirling it, at this point, I'm seeing mostly green, but I do see pockets of blue. If I keep adding sodium hydroxide, well, guess what? Eventually, we're going to get an entirely blue solution. But swirling does the trick. So right now, I see a pocket of blue at the bottom where the acid has dropped because it's a denser liquid. I'm just going to swirl for a little bit here until we get some mixing. And by now, we're kind of back to a light green. If I add a few more drops of the sodium hydroxide, note the blue color again. And eventually, if you add enough of the base and mix it enough, you'll get an entirely blue solution. And you can even change it back. So let's say, well, I want to get it back to green. I can add some acid. And I could make it green. And if I continue on with that, I could even make it yellow again. So the point here is the equilibrium can be found based on the pH of the solution surrounding it. The idea is we're making an actual equilibrium with observable colors. And you can shift it. And chemists do this all the time. Chemists have an awareness of equilibrium reactions. And so they decide, well, I need this much of a product. And so I'm going to take action so as to make more of the product or less of the product. And that's kind of the point of the lab, is we're the chemists and we can decide how much of a substance we need. Okay, students, let's take a look at the data for the Shifting Equilibrium lab. First of all, in part 1 of this lab, we performed this reaction. We took iron 3 ion that was delivered by iron 3 nitrate. We reacted it with thiocyanate ion delivered by the potassium thiocyanate solution. In mixing those two, we produced a dark red iron 3 thiocyanate, a dark red complex ion. This reaction produces a product that's dark red in color. So the darker the test tube appears, the more product we've formed. The lighter the test tube appears, the less product we've formed. So a shifting to the right means it's darker. A shifting to the left means it's lighter. The other really important point is that this is an exothermic reaction. So it's as if heat is one of the products along with the complex ion. That's going to help us understand why the heating changed the color of the solution and the cooling changed the color of the solution. So let's take a look at the data table. Based on what we saw, the initial control solution was kind of a red color. We saw some of the product formed. When we added iron 3 nitrate, we were adding additional ions of iron 3. That is, we were adding more reactant to the mixture, which in effect pushes the solution to the right. And we saw a darker red color after adding that reactant. Similarly, when we added some potassium thiocyanate, we were also adding reactant. If you add more reactant ions, in this case thiocyanate, you're also pushing further to the right. So we saw a darker red. That is, more product was formed. When we cooled the solution, now remember, it's an exothermic reaction. So if you're taking something on the product side of the equation, let's treat heat as if it's a product, and you're removing it, we actually produced more product. Again, it was darker red. But when you heated it, that's as if you're adding more product. So the shift in Le Chatelier's principle would be away from the product. We saw a lighter red compared to the control. Lastly, by adding sodium bisphosphate, what we were doing is sucking out, we were adding, we were reacting away one of the reactants, and that drove the reaction dramatically to the left. It got to the point where it was kind of a cloudy whitish color. So I would say this was a much lighter red color. So a dramatic shift left. Let's go over the shifts that we saw. The control showed no shift, but if it got darker, that would be a shift right. We'll get a different marker here. So if it's darker, we're shifting right. If it's lighter, we're shifting left. So it goes shift right, shift right, shift right, and then 2 shifts left at the end. That was our part 1 reaction. Now let's take a look at the part 2 reaction with the bromescal green. In this reaction, we started with an indicator solution with just some water. We took 2 milliliters of water, we added some bromescal green. Initially, it was just a green color, so roughly neutral. When the pH of water is simply 7, so in a neutral solution, bromescal green is a green color. When we added some acid, a strong acid like hydrochloric acid, the pH dropped. Well, when we did that, the solution changed color to at least more of a yellow color, if not a completely outright very yellow color. When we added sodium hydroxide, it went back the other way. It got first to a greenish color after mixing and swirling, and then we added even more drops to get it to a blue color. Number of drops of sodium hydroxide that was needed to reach a blue color. Let's say we added about In total, it was about 10 drops. And then you could add hydrochloric acid to shift it back to green. It took about 5 drops to make all of that. If you think about this, I'd like to shift back to the original board here. In the part 2 reaction, we were also observing an equilibrium. The formula for bromesco green is kind of complicated and not very important to the understanding of what's going on. So I'm going to use, because it's an indicator, I'm going to use IN to represent that big formula. And get this, indicators are themselves weak acids. So I'm going to show the formula for the indicator of bromesco green, H, that is a hydrogen ion, IN, without revealing the entire structure. And what happens in aqueous solution is some of the hydrogen ion breaks off, and you're left with the indicator unprotonated molecule. The unprotonated molecule is a bluish color. The protonated form is greenish. And so you can play with the green and the blue and make it somewhere in between. And that's kind of the fun of the shifting equilibrium lab, is that you can make it go back and forth between different colors. Thanks for your attention.